Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at minimum spanning tree, and we will be looking at one more algorithm called Prim's algorithm. So, till now we have been looking at various applications of graphs and how to look at various algorithms of graph. So, today is also one of those days, but let us start with a real life problem. Say in India, an internet provider company wants to lay some special fiber optics cable all across India in such a way that they want to make sure that any city is connected to any other city. So, at least if somebody from one city wants to call another city via internet, it should be very fast. So, any city to another city must have a connection via the better cable line, and of course, the internet provider wants to optimize its own profit. So, it wants to minimize its cost. Now, clearly the cost happens because of the amount of cable laid. The cable is the hard work. So, it wants to minimize the length of the cable laid. So, this is the problem. You can imagine that such kind of problems occur in almost a day to day basis all across the whole planet till right now. So, how do you solve such a problem? So, as I told you earlier, for this kind of situations, as you have seen, graph algorithms helps, or modeling it in terms of graphs helps a lot. So, for a graph we have n vertices v1 to vn, and we have edges which are pairs of vertices e1 to em. Now, graphs are very nice mathematical objects. They help in understanding the relationship between objects. They are very simple and general. Many problems in real life can be modeled after as graph problems, and studying the structure of the graph can help in many real life situations. So, for our problem, so let us consider that we have these 7 cities A, B, C, D, E, F, G. Between each city we can have a path or not path. So, if there is a road from A to D, we draw a edge between A to D, and we can also put some weights on these roads depending on the distances. So, thus we have these distances between roads. This describes as the whole instance of the problem. So, we have the cities, we have the distances, and we have the distances of the roads, which basically tells us how much cable is required to be laid between two adjacent cities, and the goal is to select as few edges as possible, or select some set of edges such that any two vertex there is a path using those set of edges, and we want to minimize the length of the total cable laid. In other words, we want to minimize the weights of sum of the weights of all the selected edges. So, a graph where we have any two vertex, there is a path from between them, this kind of graph is called a connected graph. So, basically what we want is that we want a sub graph which is connected. We want a subgraph which is connected and whose total edge weights is minimized. To understand this better, let us look at trees. So, tree is kind of fits into our problem perfectly. A graph G is called a tree if it is connected and it is minimal, in the sense that if I remove any edge from that graph, the graph becomes disconnected. So, this definition is equivalent to saying that this graph G has no cycle. It is not very hard to see that if the graph has a cycle, then that cannot be minimal, because we can remove an edge and obtain a smaller graph which is connected. The another equivalent definition is that G has n minus 1 edges. So, in other words, a graph G is connected. If a graph G is connected, then it is a tree if and only if it has n minus 1 edges. So, in other words, what we are looking for is a minimal connected subgraph of this graph G, or in other words, we are looking for what is known as a spanning tree. So, given a connected graph G, a spanning tree is a subgraph of the graph which is a tree and touches all the vertices of G. So, this is also minimal connected subgraph of G. We can also have weights on these edges as we have in our problem, and in that case we can talk about the total weight of the edges of this spanning tree, and the spanning tree with the minimum total weight is known as the minimum spanning tree. Note that in a graph there can be more than one spanning tree and more than one minimum spanning tree also. So, for example, here is an example say. So, I have these edges and I have this weights on these edges. We can have various kind of spanning trees. For example, this is a spanning tree whose weight is 54. Now, why is it a spanning tree? It touches all the vertices and it is a tree because it does not contain any cycle. We can also have another kind of tree which is like this, whose say weight is 45, and then we can have weights another one which is edge is this one which is weight is 39. Note that there can be many other spanning tree. So, the problem is given a graph G and a weight function that puts weights on these edges. The weights can be negative or positive, and we want to find the minimum spanning tree. So, in the last lecture we had seen one such algorithm. In particular, just like divide and conquer and dynamic programming, we were considering a new technique of algorithm called greedy algorithm. While in the case of divide and conquer and dynamic programming, designing the algorithm is hard, but proving it is more or less simple, or at least kind of intuitive why it is right. In the case of greedy algorithm, it is not the case. It is something like one will solve something in a greedily and hope that the algorithm outputs right answer. So, in other words, we just would like to greedily solve the problem and will output the right answer. So, we will use greedy algorithm to solve the finding minimum spanning tree. So, in the last lecture we saw one such algorithm called the Kruskal's algorithm. So, in Kruskal's algorithm, the idea was pick the minimum weight edge. Now, pick the next minimum weight edge as long as it does not causes a problem, or in other words, as long as it does not creates a cycle. Then pick the next minimum weight edge and pick it if it does not create a cycle, and so on, keep on doing it as long as possible. So, here was the pseudo code. To understand whether we are creating a cycle or not, we were storing for every vertex v, we are storing a set S v. S v was the set of all vertices that are connected to v by the already selected edges. Now, we are sorting the edges in an ascending order. We pick the next edge that we have not selected by order of the weights. If they are both in the two sets are not equal, or in other words, if u is not connected to v otherwise, I will add this edge or select this edge, and I will upgrade the SU and SV sets accordingly. It was an easy algorithm as such. It is clearly a greedy algorithm because it just does everything in a greedy way. It picks the minimum weight as much as possible, but the correctness proof of this algorithm was a bit complicated. In fact, it was not clear also in a first shot that whether the output algorithm is anyways connected, and secondly whether it creates a cycle and so on. Anyways, we had seen this proof of it in the last lecture, and we have seen that that algorithm takes order e log e steps. The main amount of time required is in the sorting of the set of edges in an ascending order, which takes order e log e. So, question is that can we do better? The answer is yes, we can do better. Again we will use another greedy algorithm, and we will try to just use a different kind of greediness to solve it. So, here this algorithm is known as the Prim's algorithm. So, this is very similar to the Dijkstra's algorithm. Note that in the case of Kruskal's algorithm, we were not sure whether the graph is connected, because we were just picking up the minimum weight edges, and there are no guarantee as such that the graph is always connected. But here what the idea is that we always try to ensure that the graph that we have selected till now is connected. So, we start from any vertex V s, and then we pick the smallest edge that is adjacent to any vertex in S. We initialize it, we start S with as any vertex, and every time we look at the minimum weight edge that is going out of S, we will pick that edge and we will include it in our tree. At the end, if I have an edge and that creates a cycle, then that is not good. So, in that case we cannot do it. So, how can we check whether a cycle is created or not? Just like the last step, last case, if the two vertices of the edges are of same color, or in this basically if they are connected already, then they will create a cycle. So, here also, since we always ensure that the graph that we have created till now is connected, so all we have to check is that whether the new edge that I am trying to add is joining two vertices in the same connected component or not. So, this is the idea of the Prim's algorithm. So, let us take a short break now. After the break, we will see the Prim's algorithm and analyze the Prim's algorithm. Welcome back after the break. Before the break, we just saw the idea of the Prim's algorithm. So, let us see how does it work. So, here is a run of the Prim's algorithm. So, we have this graph G. Now, we start from any vertex. In this case, we start from say vertex D. In the first step, we look at all the edges going out of D and look at the smallest edge weight. In this case, it is just 5. So, we take that edge and we colored that vertex also. Now, my current graph is this graph AD. So, we look at all the edges that goes out of AD and we will pick that edge. We have this edge 7, 9, 15 and 6. So, the next weight must be 6 and we will pick that edge 6. So, when we pick that edge, we again colored the vertex that we have seen red. Now, vertices that we have seen are A, D and F. We look at the edge that goes out of A, D and F and say in this case it is 11, 8, 15, 9 and 7. So, it must be the H 7. So, we pick that H 7. Now, once I pick this H 7, this becomes red, and then all the edges between this vertex and any other vertex which is already colored red are basically blanked out or has been marked not possible. Or in other words, we will just go over all the edges of B and look at which of them are colored red and remove them, because they will never come in the picture, because if I ever take this vertex edge B D, then I will have create a cycle. So, that is not possible. So, now say my graph is A, B, D and F, and at this point we look at again all these edges that goes out of any of this thing. So, it can be the 8, 7, 15, 8 or 11, and in that case we can choose this 7 because that is the minimum. So, we will choose that minimum 7. Again we will color this edge E red, and once we color this edge red, all the other edges between E and any other red colored vertex is marked out. And again we look at all the edges, and then we see that 5 is the minimum weight, and we pick that one and color them, and again we see this 9 to be the minimum and we choose this. So, this is our Prim's algorithm. You can verify for yourself that this is actually a minimum spanning tree in this example, but we need to prove that Prim's algorithm will always output a minimum spanning tree irrespective of the example that we are picking up. So, like any greedy algorithm, proving that one is always the hard part. So, here is the Prim's algorithm. So, we start with this edge u, which is a set of vertices that are colored red. As long as this we are not colored all the vertices, we will pick the smallest cost edge out of u. So, the one of the vertex is in u and the other one is not in u. We add that edge to our selected edge and add the v to our u, or rather color the edge v as red. The algorithm is again very simple. We have to check the correctness of this algorithm. Why is this graph connected, and is this graph has a cycle, and so on. Connectedness and cycle is slightly easy in this setting. Note that we have always ensured that we keep on doing it till all the edges, all the vertices are colored red, and whatever we choose are edges going out of the set u, or set of colored red colored vertices. So, at any point of time the set of selected edges forms a connected graph. So, I will always ensure that I have a connected graph, and at the end of the day I would have touched all the possible vertices. So, the algorithm will always output a connected graph. What about the tree structure, or in other words, will that be a cycle? It cannot be, because every time I am picking a edge from one which I have seen before and to one which I have not seen before. If I have not seen before, then how can I get a cycle back? So, the no cycle, the tree structure is also ensured. The fun starts when we look for this minimum, proof that it is an MST. For that we have to look at the properties of the trees. Let us quickly revise it, that if I have a tree and I add an edge to that tree, then I get a cycle, and if I remove any edge from that cycle, we get back a tree. This is a very crucial part of this whole thing, and also there is a unique path between any two vertex in the tree. So, we have to understand, is this an minimum spanning tree? So, let T 1 be an MST, some minimum spanning tree. Where does T be the tree obtained from the Prim's algorithm? Now, in the Prim's algorithm, I kept on picking edges one after another. Let us consider the first edge that I have picked, which is not in T 1. At some point of time that must have happened, maybe that is the very first edge that I picked, or maybe it is somewhere in the middle, does not matter. But consider the first edge picked during the construction of T. So, that is not in T 1. So, remember that is exactly how we did it earlier, and let it be the edge u v. Now, when this edge u was selected, note that u was in colored and v was not colored. So, let us try to understand where we are now. So, here is this tree that we have. Let us just assume that this is T 1, which is the minimum spanning tree that we have. Now, there is one edge, that this be an edge that is the first edge that we are talking about, which our Prim's algorithm has chosen, but is not there in the original, in the actual MST. So, what we do is that we add this edge to this graph. Notice when we add this edge to this graph, we get this path. we get the cycle that has been created. Now, when this edge was picked up, one of them, let this be u and let this be v. So, this one was chosen already and this one was not chosen. So, consider the path that from u to v. Now, in this path, if there exists a edge that is more than this edge, then I can add this red edge and remove this edge, and then I would get a tree that is a smaller MST, spanning tree with a lesser weight. So, that cannot be. So, that means all of them, all these edge weights on this graph must have been less than or equal to this weight of this red edge. So, what I do is that I will take this edge, and in that case note that in Prim's algorithm this edge, one of the edges must have been possible for selection. So, let us say this edge, I have chosen this red edge over this black edge because this red edge had a smaller weight than the black edge, but that cannot be, because if it is smaller weight, then I can add this red edge and remove this black edge, and then I will get a spanning tree which has smaller weight than T 1. So, that cannot happen. So, in other words, we can prove that if I have a spanning tree, it will match this new MST, this Prim's algorithm perfectly. So, that kind of shows that the Prim's algorithm will indeed output a minimum spanning tree. How about the runtime of this algorithm? The runtime algorithm is exactly same as the Dijkstra's algorithm. Note that every time we have to pick the minimum of all the edge weights that are minimum of all of them, that will take order v steps, and we output the run it for till we have chosen v number of edges or colored v number of vertices. So, in other words, so the total runtime of this algorithm will be order v square. If you do use some advanced data structure like Fibonacci heap, then one can improve it to E plus v log v. Note that this v square or this v plus E log e is better than what we got for the Kruskal's algorithm, which was order E log e, because e can be of the order v square. So, we have removed a log v factor. So, in other words, to summarize, for the minimum spanning tree, we have a Kruskal's algorithm that runs in time order E log e steps. We also have a Prim's algorithm that does slightly better in order E plus v log v steps. Both these algorithms are greedy algorithms. Getting this algorithm is easy, but proving the correctness of the algorithms are the hard part of this algorithm. In this lecture, we looked at the minimum spanning tree problem and Prim's algorithm, which is a new algorithm. We come to the end of graph algorithms. In the next few lectures, we will be looking at mostly on some other non-graph algorithm problems.